In this episode, we are going to solve tutorial questions in fluid mechanics, chapter 1. So let's take the question. We are going to be fast about it. The dynamic viscosity of air at 15 degrees Celsius is given as this. Using Sutherland's equation, find the viscosity at 100 degrees Celsius. So we have the viscosity at 15 to be this. We have to find the viscosity at 100 using Sutherland's equation. Do we recall the Sutherland's equation? Yes, which is mu on mu naught should be equal to T on T naught. Pay attention to the equation. This is 3 on 2 multiplying T naught plus X, another T plus S. This is the Sutherland's equation. So to use this equation, we have to find the viscosity at 100 degrees Celsius. First, let's list the parameters given. So at 15 degrees Celsius, look at the question. The dynamic viscosity, which represent the mu's, T represent the temperature, and S represent the Sutherland's what? Constant. Are we good? S represent the Sutherland's constant. So we saw that when we were tackling the tutorial or those explained ones, we saw that mu naught is the initial what? Viscosity, whilst mu is the what? Viscosity we are going to look for. T is the temperature at where we are looking for the mu, and T naught is the initial what? Temperature. So looking at the question, we have our initial temperature to be 15, which is our T naught. And here we are working in Kelvin. Remember, everything supposed to be in Kelvin. So 15 degrees Celsius, to convert to Kelvin, we add 273, which is going to give us a value of what? 288 Kelvin. At this temperature, its viscosity is that, which is the mu naught. Pay attention, please. And that viscosity is 1.78 10 to the power negative 5 Newton second per meter square. Using Sutherland's equation, find the viscosity at 100 degrees Celsius, which is our T. So our T is given as 100 degrees Celsius, but to Kelvin plus 273. And that is going to give us what? 373 Kelvin. Okay, so the Sutherland's equation, the S is a constant for every gas. Are we good? Remember, this equation works for what? Gases. And we have a table for the constant. For air, because we want to know the viscosity for air at a certain temperature. For air, the Sutherland's constant X is given as 111 Kelvin. So we can use this as the constant. So straight away, we can punch in the values and know the viscosity at 100. So here we are looking for our mu on, what is the mu naught, which is giving us 1.78 10 to the power negative 5, which is equal to, we have our T. From this, our T is 373 on T naught, which is 288 to the power 3 on 2, multiplying this T naught, which is 288 plus the constant. All right, so this is it. And we are looking for this. It's very simple. So with your calculator, you can punch everything here. And when I punch everything here, I'm getting mu still on 1.78 to the power negative 5 equal to, everything here from my calculator is giving me 1.2151. Therefore, my mu is 1.2151 multiplying 1.78 to the power negative 5 for that. And with this, you are going to get your mu to be 2.163 times 10 to the power negative 5 the unit Newton second per meter square. And you can conclude that, therefore, the viscosity at 100 degrees Celsius is 2.163 to the power negative 5 Newton second per meter square. Are we good? So this is how we go by using the Sutherland's equation. Remember to convert the temperature to Kelvin, where you're given the initial temperature should always be T naught, and the next temperature will be the T. The first given viscosity will be your U naught, and what you are looking for will be your U. Are we good? Let's look at the next example. The absolute viscosity, and remember this mu that we are talking about, either mu naught or mu, they are referred to as what? Absolute viscosity. Remember, we have kinematic what? Viscosity. We'll talk about that, which is represented by V or V naught. But here we are talking about absolute, so pay attention. The absolute viscosity of propane, a gas, at 100 degrees Celsius. So first, I'm getting my temperature T naught to be what? 100 degrees Celsius. So to Kelvin, 273. And that is giving me what? 373 Kelvin. So the viscosity at this temperature is 1.00 to the power negative 5, which is my mu naught, because they are initial what conditions, which is 1.0010 to the power negative 5 Newton second meter square. And at 400 degrees Celsius, which is my T, which is 400 degrees Celsius plus 273, and I'm getting what? 600 and what? 73 Kelvin. Are we good? So at this, the absolute viscosity was also given as this. So what are we looking for? Find the Sutherland's constant for propane. Wow, here we are looking for the S, the constant. So my mu was also given as 1.72 to the power negative 5 Newton dot second per meter square. Are we good? So we have that, and we have to look for S. And we can only do this using what? Sutherland's equation. So first, straight away, we write our Sutherland's what? Equation in absolute viscosity. Remember, we have Sutherland's equation in what? Kinematic viscosity. We will get there. So using the absolute viscosity, that's what we know. This is the equation. Our mu and our mu naught is giving us our T on T naught, 3 on 2. So straight away, this is our equation, and we are looking for this x. We have all the parameters, we can put them in and solve for s straight away. So first, my mu is giving us 1.72 to the power negative 5, or my initial one, which is 1.0010 to the power negative 5, should be equal to my t was given us what? 673, and my T naught is 373. Don't forget 3 raised to the power 2, and I have also 373 x 673 on what? X. So this is just change of subject. You can just make it. Do your substitution and go ahead and you punch this, you are going to get 1.72 equal to, I will punch this one too, and I'm getting 2.426 multiplying 373 plus x on 673 plus x. Are we good? So I can divide both sides by this to take away that. So when you divide both sides by 2.426, here by 2.426, this divided by this, I'm getting 0.708992. So this is just mathematics. You follow the procedure and you understand it better. We are looking for S, so we can do cross multiplication. This is over 1. So this is the same thing as 0.70899 multiplying 673 in one bracket plus multiplying that 0.70899x equal to 373 plus s. We group like terms, we have those here, and I can also send the x here. So in all, I can get my value to be 0.70899 multiplying this 673. This will come minus 373 equal to x. This will go minus 0.70899x. How we go? So you can factor s out. Therefore, our x will be equal to 0.70899 multiplying 673 minus 373. Everything on 1 minus 0.70899. And when you punch this, your S, Sutherland's constant for your propane is 358 from here. But on tables, you will get it as what? 360 Kelvin. There we go. The approximations from this side, the approximation from this side will cause an effect in this. But you are close to the constant, which is very okay. So in case you are to solve for the constant, you have to solve for any one missing parameter. This is the equation. You just do substitutions and you go. Let's check it out. Equation that involves the kinematic viscosity. How is the equation like? Let's see. So using Sutherland's equation and the ideal gas law, develop an expression for the kinematic viscosity V on V naught in terms of pressures, that's P and P naught, and temperatures T and T naught, where the naught refers to the reference conditions. So P naught means the initial pressure given the initial what? Viscosity, that's the kinematic viscosity, and T naught represent the initial what? Temperature. How do we, you see, for the Sutherland's equation, let's see, U on what? U naught equal to T on T naught 3 on 2 multiplying T naught plus S on T plus S. This is the Sutherland's equation. There is no pressure given, no pressures. So we have to develop another equation with pressures and with what? Now, we are not going to relate it to the dynamic viscosity again, but here it will be in terms of what the kinematic viscosity. Pay attention. And the question is saying we should use only two equations using Sutherland's equation and the ideal gas law. But we've already discussed this equation. So this is the equation 1 for the Sutherland's. What about the ideal gas law equation? We saw that from the ideal gas equation, our P, our pressure is given as what? Rho RT. This is it. Are we good? So from here, I can make rho the subject. That's density, which is pressure on what? RT. Pay attention. So we are proving the formula to get transform this equation into a form kinematic viscosity involving pressure, temperature, and what? Sutherland's constant. So this is the starting point. I have it. This is the ideal gas equation. So I make density the subject and I'm getting this equation 3. Are we good? But since we are going to transform dynamic viscosity to what kinematic, we know the relationship between them. We know that the kinematic viscosity V is giving us mu on what? Density. Are we good? So can we say that then if I'm bringing to remove this and bring V, I can say mu is equal to V and what? Rho, which is the density for this part. Then for the naught part, can I also say will be V naught on what? The density naught. Are we good? So we can continue from this. Then let's put in place here these values. Okay, so in place of the mu, can I say I'm getting, pay attention, so we are proving the equation. I'm having V on what? Rho, which is the density. For these two, I'm having V naught, rho naught. Then not just represent that always these given values will be the what? Initial conditions. Are we good? Equal to everything in the Sutherland's equation. T naught 3 on 2, T naught plus X, and T plus S. Are we good? But we know that our rho is also giving us pressure over RT. Remember, in the ideal gas law, the R is a constant for what? The gas. And here we are talking, this equation works for a particular gas. So within that gas, the R is what? The same. So if rho is giving us that, can I also say that rho naught will be also at P naught on, since R is constant, just R, but the temperature will be what? T naught. So I'll bring it in place of what? This ones. So here will be my V multiplying the whole of what? This. That's pressure on RT divided by this. So I'll say divided by V naught P naught on RT naught equal to this whole thing, T on T naught, 3 on 2. This is a typical quiz or an exam question where you have to prove. So I will transform this to a multiplication sign so that it will reciprocate. So Vp on what? RT will be times RT naught on what? V naught P naught. This R will take care of this R, equal to the whole of T on T naught. So this R has taken care. So our final equation now, not our final, but from here we are getting this V, this P, and this T naught, right? On here too, we have this V naught, this P naught, and here the original T will be equal to our T on T naught, 3 on 2. Then T naught plus S on T plus S. Remember, the question is saying we should express it in such a way that one part of the equal sign would just be V on V naught. In terms of express the equation so that V on V naught will be in terms, meaning equal to a certain P naught, a certain T naught. So we have to take care of what? Take the T naught from this side of what? The equation. Are you good? So that we will be left with only the V naught. So what do? We have to divide both sides of the equation by this whole thing so that it will cancel out. Are we good? So let me make it properly. So here we can continue as our V on our V naught as 1 multiplying, we had P and what? T naught, and we had P naught as what? T equal to all right. So I'm dividing both sides by this, by that, so that the final part will be I'll be left, when I divide both sides by this, I'll be left with V on V naught should be equal to, remember this is multiplication, and when you are bringing a division 10, the order matters. So I'll just put the whole of this in one bracket and say T on T naught, 3 on 2, T on X, it's closed. It's going to be divided by this, divided by that, which is P T naught on P what? P naught T. I want to convert everything into multiplication, so I'll just change this to multiplication. So I'm getting my V naught to be, since multiplication, the order does not matter, I can remove this big bracket, so that I'll get in terms of T on T naught, 3 on 2, multiplying T plus S. So I'll change this to multiplication to reciprocate, giving me P naught T on P and T naught. Are we good? All right, so can I further express this again in a certain form? So to express that, I say V on V naught should be equal to this T on T naught, 3 on 2. Then T naught on S and T plus S. This can also be expressed as T on T naught. Then I also have P naught on what? P. I'm splitting this. But look at this. We have like terms. T on T naught, T on T naught. Since there's multiplication, law of indices, we can add the powers. Are we good? So can I say V on V naught is equal to, now this will be T on T naught, the powers, this is raised to the power 1, 1 plus 3 on 2, and multiplying this T naught on X, this T plus S, and still the pressure on what? P. So if we add 1 plus 3 on 2, we are getting 5 on 2. So V on V naught will be our T on T naught, 5 on 2, then T naught plus X, T plus X, P naught on P. So finally, this is the equation we are looking for. So I can better still make it a simple equation in such a way that my V on V naught will be equal to the pressure P naught on P, multiplying this T on T naught, here 5 on what? 2, multiplying T naught plus X, T plus S. So this is the equation we are looking for. So now this is expressing the kinematic viscosity in terms of pressure, in terms of what temperature, and in terms of what? The Sutherland constant. So here, V naught, P naught, T naught represent the initial condition. You see, with the Sutherland's equation, which involves this, know the difference between the two equations. This is just the Sutherland's equation, and that is 3 on 2, and that is T naught plus S and T plus S. With the Sutherland's equation, we have 3 on 2 here, no pressure involved, but here pressure is involved with 5 on what? 2, and even this V is the kinematic viscosity, and this U is the dynamic viscosity. So pay attention when you are giving the viscosity as what? Dynamic viscosity, meaning you are going with this. If you are given as kinematic viscosity, definitely they will give you pressure, and you are going with this equation. So let's solve an example so that we see how we will use this equation. It's very simple and we will love it. Okay, so the kinematic viscosity, so you see we have the kinematic viscosity of methane at 15 degrees Celsius. So can I list my parameters? So at T naught, which is the first parameter, T naught is equal to 15. I will convert it to Kelvin. If you are given in Kelvin, then no need to convert again. So the kinematic viscosity at 15 degrees Celsius and atmospheric pressure is this. So this is the V naught, the kinematic viscosity, because it's the initial one was given, 1.59 to the power 10 raised to the power negative. And even the unit should tell you that we are working with what? Kinematic viscosity. With the mu, its unit is Newton dot second per meter square. And with the V, it is meter square per what? Second. Are we good? So the condition, the kinematic viscosity at T naught and atmosphere. Remember, atmosphere pressure, meaning our P naught is what the atmosphere pressure. And no value was given. And atmosphere, which is 1 atmosphere pressure, 1 atm, is a pressure was given. Using Sutherland's equation and the ideal gas law, which is the combined law to get that equation we just made, find the kinematic viscosity. So we have to find V, which we don't know, at T, which is equal to 200 plus 273, which is 473 Kelvin, and 2 atmosphere, which is pressure. So, and the P is also what? 2 atm. So here, basically, we have everything. We are only left with what? The V. And from the Sutherland's equation and the ideal gas law, this is the Sutherland's equation, or this is the equation we established, which is V on what? V naught equal to our P naught on P multiplying our T on T naught 5 on 2, our T naught plus S, and our T plus S. So we have everything. You can just input and find the what? The V. So V will be on V naught, which is 1.59 to the power 10 negative 5. Our P naught was what? 1. And our P, 2. So as that. And our T, which is what? 473. Our T naught, which is 288. And remember, it is raised to the power 5 on 2. T naught 288 plus S. What is this? Is a gas, methane. From tables, it will be given to you. The S for methane is giving us 198 Kelvin. It's just a constant. So you should either have the table and read it from, or the question should give it to you. 198 on our T, which is 473 plus 198. And straight away, if I punch everything here, I'm getting my V on 1.59 to the power negative 5 equal to, I'm getting 1.25186 from the whole of this. Therefore, my V will be 1.25186 multiplying that. 1.59 10 to the power negative 5. And with this, we are getting 1.99 10 to the power negative 5. Check your unit, meter square per second. So the kinematic viscosity at 200 degrees Celsius and 2 atmosphere is giving us what? This. Check the equations. They are what? 2 different equations. This involves pressure. The one involving pressure only involves what? Kinematic viscosity. And the Sutherland's involves the dynamic or absolute what? Viscosity with no pressure. Thank you for watching the first part of this episode. Check out for the next part, which is also the second set of tutorial questions. Very difficult and amazing ones. Thank you.